will discuss the results of Fourier transform EPR. Okay, so moving on. So just a minute. All right. Sorry for the inconvenience. So Hyper instrument is a unique pulse spectrometer at 94 gigahertz. This instrument has a 1 gigahertz instantaneous bandwidth of 93.5 gigahertz to 94.5 gigahertz. And the instrument doesn't employ any sample holder. So this instrument is a clone of Hyper, located at University of St. Andrews. So this is the Hyper image at the MagLab and postdoc CRISPR scale. And this is the schematic of quasi-optics. The quasi-optic components provides a good isolation between the source sample and the detector. Primarily, the bandwidth of Hyper is limited by the 1 kilowatt amplifier, which limits it to 1 gigahertz. And this amplifier provides sufficient microwave power to have a nanosecond time resolution and high concentration sensitivity. So in addition to that, we also have arbitrary waveform generator that provides us with complex waveform shaping. And recently we have installed a piezo-controlled crystal rotator that helps with single crystal rotation studies. So this recent upgrade is not relevant to the current talk, but this is something new and exciting I wanted to mention. Okay, so this is the schematic of AWG implementation on the Hyper. So all the signal processing is done at the low frequency. We have base frequency of 7.6833 generating from the local oscillator, which gets multiplied by 12 times to give 92.2 gigahertz, which is then mixed harmonically with a 1.8 plus or minus a sweepable offset from the AWG, resulting in a 94 plus or minus the sweepable offset frequency, which is then amplified with the Claystone amplifier, then passed through the quasi-optics to the sample. The emission signal from the sample is detected after being down converted in 2 steps. So first with 92.2 gigahertz, resulting in 1.8 plus or minus delta gigahertz, and which is then mixed with a 1.8 gigahertz from the AWG, giving us a in-phase and a quadrature detection. And the local oscillator on the AWG is synchronized with a 10 megahertz clock. So what can we do with this AWG? So we can design pulses to have, for instance, like we can have a Gaussian pulse for narrow excitation. Here we have a 100 nanosecond pulse, which has an excitation bandwidth of about like 50 megahertz, then which we can use it to excite a really narrow portion of a broad spectra. So in contrast, we can also excite across the whole bandwidth using a frequency swept pulses. So there are several window function for this frequency swept pulse, but we use the worst window function, which is a wideband uniform rate smooth truncated one, which is given by this amplitude function. Here how smooth the rise and fall of this window function is determined by this exponent n. So if you have a chirp width of 500 megahertz, then we excite a spectra uniformly about 500 megahertz. That means if we have a radical here, the temporal radical, which spans 500 megahertz, then we can excite the whole spectra using these frequency swept pulses. Typically, we would like to have a uniform excitation bandwidth. So which means we don't want microwave to have a frequency dependence when it reaches the sample. So although we do not use any cavity, the output from the EIK amplifier itself has a frequency dependence, which is given by this blue trace. So with the AWG, we can compensate for this by giving a different microwave power for different frequency. So as a first guess, we just took the reciprocal of this blue function. Then we measured the output from the EIK. Then we did this back and forth by like 4 to 5 times until we obtained a much flat profile. So flat profile from the EIK output. So once we have this correction function, we can then multiply it with the worst window function, so which guarantees us that we have a uniform excitation profile. So before moving on to the results of Fourier transform EPR, so let me just briefly discuss on the magnetization response under chirp pulse. So let us consider a chirp pulse centered about omega c having a width of omega SW, that's the sweep width, and a pulse length of TP. And the chirp rate is the ratio of the sweep width over the pulse length. So here I've considered the semi-classical block equation without any relaxation. So where the B of t is sum of the static field and the incident microwave pulse. So converting into angular frequency, so in the laboratory frame, we have this equation. So it is more convenient if we go to a rotating frame. So by transforming to rotating frame, we obtain a time-dependent offset along z direction and omega 1 along x. So this time-dependent is the difference between the Larmor frequency and the microwave frequency. So now, if we choose our center frequency to be on resonance, then this time-dependent offset depends only on the time and the chirp rate. So essentially, which means the spin vector or the magnetization vector processes around this effective field. So now, if we want to flip the magnetization from, let's say, plus z to minus z adiabatically, so we have to follow some criteria, or the chirp pulse has to follow some criteria. This criteria for adiabaticity is given by these two conditions, which has been mentioned by Alex Paynes back in 1985. So the first criteria tells us that the rate at which this effective field tips has to be much lower than the precision frequency of the magnetization vector. So which is given as by the criteria 1. And the second criteria is easy to understand, which says that so the magnetization goes from plus z to minus z. So in order to quantify the criteria 1, we define a dimensionless factor called adiabaticity factor as the ratio of effective field over the rate of change of this tip angle. So for the linear chirp, so we obtain this equation, and so then we can quantify it by calculating the minimum adiabaticity at the center of the pulse. So that is at t equals to 0, which we get as the ratio of square of the nutation frequency over the chirp rate. So this gives a guideline to form these the adiabatic in designing these adiabatic chirp pulses by choosing the microwave power or varying the pulse width or the pulse length. So the group of Ganoy-Eshke recommends that to have a minimum adiabaticity of about 5. So this is the simulation we can do using this SPIDIAN package. So here, so we have done the spin excitation under a 300 nanosecond burst pulse with a 1 gigahertz sweep width. Here we see that the magnetization going from -1 to +1 adiabatically. And so this is the spin trajectory in the rotating frame, where the similar again in it's going from -z to +z. So having seen the hyper instrumentation and brief theory on adiabatic pulses, so let us apply this the frequencies of pulses to do broadband excitation and detection. So this is this work has been published in Applied Magnetic Resonance last year, and I'll be presenting it now. So typically in a pulse EPR, we can apply a Haneko sequence, and which results in a echo, and then we sweep the field or the frequency to obtain a echo detected field sweep or echo detected frequency sweep. So in this case, this so we did this Haneko sequence on a temple, which is dissolved in a equal proportion of water and DMSO. And we chose the temperature at 50 Kelvin to have a reasonable spin lattice relaxation time. Now, as we can see, the spectral bandwidth is about 500 megahertz, and the instrument bandwidth is about 1 gigahertz. That means we can apply a broadband excitation pulse to excite the entire spectra, and we can detect it. So to do that, we employ this Bodenhausen pulse sequence. So one subtle thing between this and the Haneko sequence is the initial excitation pulse is twice the length of the refocusing pulse. So this can be understood as the spin packets on the low frequency regime is under free evolution for much longer time compared to the spin packets at the high frequency end. So in order for those spin packets to refocus at the same point, so we arrive at the condition that the excitation pulse have to be twice the length of the refocusing pulse. So in this one, we apply a non-adiabatic pulse. So that means we keep the minimum adiabaticity much lower than 1. And such pulses are termed as fast passage pulse. So this is the result from our experiment, where we chirped from 93.5 gigahertz to 94.5 gigahertz of about length 700 nanoseconds. And so as we can see from this figure, so the features we get from the Fourier transform spectra is almost same as we get from the Haneko sequence or the echo detected field sweep spectra. I apologize, I didn't mention, I mean, when we obtain the echo here, so we select a window and we do the Fourier transform of this echo. So that would result in this spectra. So it's worth noting that this is a one-shot experiment. So we wait for like 10 minutes, depending on the average, and the repetition rate, but it's typically takes about like 10 minutes. And also, so we use the nutation power of first pulse is 16 times smaller than the nutation frequency of second pulse. So this one is a bit tricky. If we want to carefully choose the power of the first and the second pulse, we will have to do numerical simulation considering the relaxation. But we didn't do that. We just choose this number based on the visual appearance between the Fourier transform detected spectra and the echo detected field strip spectra. So now we can excite and detect the entire bandwidth of tempo. So now we can do some relaxation studies. So what we do here is, so we apply a adiabatic inversion pulse to flip the entire spectra. Then we vary the delay between this inversion pulse and the detection pulse. So as we do that, we see that the spectra, which gets flipped initially, decays rapidly and recovers back to equilibrium gradually at a time. And one thing to note that is this is on a logarithmic scale. So these are the pulse length of 10 microsecond and nutation frequency of 16.5. So which gives us a minimum adiabaticity of about 25, which is well above the minimum adiabaticity criteria. So one thing to note here is we could not efficiently invert the spectra, the amplitude, which is about like 0.8 here. And it could be because of the relaxation. It is because of the phase relaxation of the spin packets. Now, if we plot a 2D false color plot, so we can see that different part of the spectra passes through the 0 point at different time. So that means there's a clear variation of relaxation as a function of frequency or the G values. And we also notice some inflection points across the nitrogen hyperfine components. Now, if we take the echo intensity at each frequency as a function of this relaxation time or the delay between the pulses, then fit it to an exponential curve as shown in the inset, then we can extract the spin lattice relaxation time. And this figure represents the T1 of the tempo across the entire spectra. So what we observe here is a clear anisotropy of the tempo across its entire bandwidth. So not only we see a clear anisotropy, we also see some dependence across these nitrogen hyperfine components. And this anisotropy in T1 is attributed to the difference or the variation in G values. So the longer or in this case, like the longer T1 is due to the shorter G values, which means small spin orbit coupling strength. So now, since we have done the T1, we also tried a T2 measurement. So we varied the delay between the excitation pulse and the refocusing pulse, and then we captured the whole spectra as a function of these delay. And this is shown in this figure here. And then, so we can do similar exponential fit to extract T2. And what we observe here is there is no dependence on T2 across the spectra. And this is likely because at this temperature, the process governing T2 is not dependent on the spin orbit coupling values or the G values. So in addition to that, to showcase the capability, we also did this pump probe experiment. So to extract the hyperfine coupling. So we do the cheesy detected NMR, where it stands for sharp echo EPR spectroscopy detected NMR, which was done by Nino Willi and Gunnar Eschke at Q band. Here we extend it to the W band. The cheesy detected NMR pulse sequence has a a initial high, you burn a hole at a specific frequency. Here is the high turning angle pulse. Then you observe the entire spectra with the Fourier transform detection. This is almost similar to the conventional LDO detected NMR, where you have a high turning angle pulse and you observe a specific frequency. And this and we vary the frequency of this high turning angle pulse. So the difference is here we keep the probe or the pump same in cheesy detected NMR, and you detect the whole spectra. Whereas in the case of LDO detected NMR, you you vary the pump frequency and you keep the same probe. So when we apply a high turning angle pulse, in this case we applied at this 94.02 gigahertz, that results in a hole burn. And in addition to that, we also observe some side holes around this central hole. And this can be understood with this simple picture here. So if we have a spin half, electron spin half, and a nuclear spin half, we get 4 levels, and which has a electron single quantum transition, and electron and nuclear, these forbidden transition corresponding to the double quantum and zero quantum transitions. So when we apply this high turning angle pulse, that results in exciting these forbidden transition, that would result in this whole kind of structure in the spectra. So one can view this cheesy detected NMR as a polarization readout that gives a complete hole pattern in a one-shot manner. So the gray trace here represents when there is no high turning angle, and the red trace when there is high turning angle. And if we take the difference between these two spectra, we obtain what we obtain from LDO detected NMR, which is quite similar. So what we observe here is the weak hyperfine coupling. So these peaks around 150 megahertz corresponds to the hydrogen, and the peaks around about like 10 megahertz corresponds to the nitrogen. So I would like to summarize by saying, so we have brought the NMR paradigm to this high field EPR, and so we did some benchmark experiments with this Fourier transform detection on a standard temporal radical, and so with this technique we efficiently demonstrated a adiabatic inversion of the entire spectra, and also measured T1 and T2 across the spectra in a one-shot manner. In addition to that, we also did these pump probe type experiments, the hole burning experiments. So the capabilities provided by this chirp pulse can also be used in this so adiabatically transferring population between the multi-level spin system, and also in coherent dynamic nuclear polarization. So I would like to acknowledge all the people involved in this work, from the group of Steve, so the John, Krish, and Johannes. And also this work was done in collaboration with Professor Graham Smith, Rob Hunter, Paul, and David from the University of St. Andrews. And also I'd like to thank Boris for integrating the SpecMan software. I think I probably rushed some part of it, but I will be happy to take any questions and answer any doubts you may have. Thank you very much for your attention.
All right. Thanks, Manoj, for this very nice talk. So I think that we have plenty of room for discussion. So given the size of the audience, I think if you have a question, you just unmute yourself and ask it out loud to the speaker. Or if you prefer, you can write it in the chat.
Hello, Manoj.
Hi.
Hi. Can you hear me?
Yes.
Oh, okay. So, yeah, first of all, it's a great talk. I really enjoyed. Okay. But I'm a CW guy. Okay. I'm not a pulse star, a high frequency guy. I'm an expand guy. Okay. So, my simple question is like, I'm not an expert in pulse. Okay. So, forgive me if I make any mistake. Okay. So,
that's okay. I mean,
yeah. My question is like, so you did this experiments at 50 Kelvin.
Right.
So that is like a solid state. The sample,
Right.
I mean, sample is a solid state, okay?
Right.
So in that case, instead of going to low temperature, can we use some solid sample at room temperature? Can we do the same experiment?
At room temperature?
Yeah, for example, okay, you have solid sample.
Yes.
So instead of going to low temperature, can we do it the same experiment at room temperature? Because the sample is a solid state,
Right. No, I understand, but I'm thinking what could affect in terms of like relaxation. I think it is possible, although I haven't tried myself at studying at room temperature. I mean, I have done EPR on some organic radical at room temperature, like BDPA, which has a fairly long relaxation time, and we can study it. That is something I haven't tried at room temperature, but I think it is doable. Unless something's if it's not limited by the relaxation.
Oh, okay. So that's what I said. Like I'm a pulse, not a pulse guy. So
right.
So I'm trying to understand the concept. Okay. So because I use X band, try to now make it as some application. That's what I do. Okay.
Right.
So now, I mean, for example, okay, instead of nitroxide, okay, there are some we call it a trityl radical time radical.
Right. Yeah.
Yes, kind of single line. It gives a single peak. So whether that kind of samples will it be more useful in this kind of technique?
Trityl, and which is really narrow. I mean, so we have tried it.
Okay. Because
so the idea here for choosing temporal radical is it's broad and it has a more features, as in like it has a clear G anisotropy and also hyperfine component. So we wanted to showcase that, hey, we have this one-shot kind of detection, and so we get the same feature that we get from doing a typical field sweep or a frequency sweep. But such narrow lines, I think we can do.
Because, for example, okay, means when you use that nitroxide, okay, Tempol, so it's a 0.25 millimolar.
Right.
If I'm correct, okay.
Yes, yeah, it's a 0.25 millimolar.
So is it like, in that case, how much volume of sample do you need? Not concentration, how much volume, like, you need something like 100 microliter or 1 milliliter, how much volume?
No, because this instrument is very sensitive.
Yeah.
You don't need really high volume.
Approximately
like 50 microliter.
Oh, okay. Good. Okay, good.
Really small, actually.
Yeah. So, but we have some other, like the trityl radical.
Right.
We have some C13 labeled TAM radical, okay? That gives 2 peaks instead of 1, okay, because the C13 splits the peak into 2. So we have that kind of samples. We study the viscosity measurement. We do use C13 TAM radical and do the viscosity measurements, okay? So what I'm thinking is like, probably that C13 TAM radical may be interesting to when I use here.
Like for like doing a relaxation study or something.
Yeah, we do. I mean, we
like
try to,
the
because
whole.
we try to use, I use that C13 TAM radical. We try to understand the viscosity.
I see.
Okay, because now means in biology, the viscosity is one of the important factor. People talk about condensate, that kind of things in biology. Right. So we try to use the C13 TAM radical, try to understand, okay, can we use EPR technique to measure the change in viscosity? So that's a kind of interesting thing. Like, you can, that's what I'm saying. Like, I'm a CW guy. Okay.
I need to think about it, actually.
Yeah. Okay, go ahead. If somebody else has a question,
I'm sorry to interrupt. Maybe we give space to other people if there are any other questions. Sorry to.
Yeah, those are good questions. Thank you.
Okay.
Manoj.
Please.
Hi, Manoj. Yeah, it was very nice, very nice talk. I have a.
Thank you.
We have also tried something similar in St Andrews, and we possibly haven't got as nice spectra as you have. So very well done. So my question is whenever, can you comment on the sensitivity? I mean, you said 250 micromolar, which is quite high concentration, and you know, and you're exciting the entire spectrum, so you might expect to have enormous sensitivity, but we've never seen that. You know, compared to a narrowband excitation, we all seem to lose a huge amount of sensitivity. Can you just comment on your experience?
I'm just going through. I don't have the top of my head, so the volume we use. I'm just checking how much. Okay.
No, I meant really the sensitivity.
Okay, yeah, I see.
I meant really the sensitivity compared to, supposing you had a standard rectangular pulse and you looked at your echo.
Right.
You know, and then you excite the entire spectrum. You might naively have thought you'd have more spins and, you know, contributing to your signal, that you'd end up with an even bigger signal.
Right.
But that wasn't our experience. I mean, can you comment on that?
Oh, in the sense, I mean, you're asking about this part where the sensitivity is almost same.
Well, I mean, the spectral shape is the same, but if you look at your echo height, for example,
you
know, relative to an echo, if you just had a narrowband excitation,
right.
I mean, maybe you didn't look at it, but
I see. I'm not sure if I'm understanding the question right, but I don't know. I mean, in our case, yeah, why we are observing.
I mean, if you haven't looked at it, that's fine. It was always something that really puzzled
something
me.
I will look at it. I mean, can you please mention it again?
So the question is, it's really the size of the echo. If you excite all the spins ideally, and you don't have.
Oh, I see. You mean like here?
Yeah, that you might expect to have an enormous echo. I mean, obviously, it's difficult to tell from that spectra, but
right.
But that's not our experience. That it was
interesting.
Very, very much down on what you might.
Might I ask what was the ratio you were using for the pulse, or the pulse length? I'm not sure if that would make difference, but so in fact we had to try few different, like many iterations of like pulse length and different ratios of the between the first and the second pulse. So maybe if that is something worth considering.
Yeah, well, maybe. I mean, the wonderful agreement you get between the field swept Hahn echo sequence and the Fourier transform is very, very impressive. I'm not sure we ever saw anything quite so good, but And if you haven't looked at it, then that's fine. I mean, I'm just, it might be interesting to have a look at, though, is just a comment.
Yeah, thank you. I will look at it.
Okay, I have a question. What is your B1 homogeneity of the sample? Can you irradiate the whole sample? And what's the...
Well, I mean, it's not homogeneous.
It's not homogeneous.
Right.
Okay.
Yeah. It's about the sample tubes we have, it's about like 2-3 centimeters. So I would say like at least we fill the tube with 2/3 of it. So it's really not homogeneous because these are like 3 millimeter wavelength. So.
Okay. And if you were to do like a square pulse,
right,
the shortest possible, what's the minimum, what the maximum bandwidth you can reach, or the shortest pulse you can have? Because of, I mean, I think there is some limitation of the like ramping of the power.
Right.
I have no idea, but yeah, what's the shortest?
We have, at least in some of the experiments, I have used really small to rotate. For example, like for a high spin system, I have used as short as like a pi over 2 pulse of like 4 nanosecond or 3 nanoseconds.
Okay, it's not okay. It's not extremely short. Okay, yeah.
But I think, I mean, of course, so Professor Smith can, because it's on hyper. So if I'm right, I guess in the paper they do mention it's as short as a nanosecond.
I see.
Right.
Okay.
Manoj, there is a question in the chat box.
Thank you.
Yeah. Could you please do the same FT approach with a broad metal center? Nice question. It's copper.
This is a good question. I haven't done on a copper. Oh, you're saying like a really broad one?
I guess so.
I mean, in principle, you could, especially, I mean, these could be, can be, I can think of using in a chirp detected NMR or this cheesy detected NMR one to find the hyperfine couplings. But otherwise, the spectral bandwidth is large compared to the excitation bandwidth. So I'm not sure if we would obtain much out of doing the Fourier transform EPR. But just to give more on this one, I have done on gadolinium actually on a single crystal where you have nice 7 transitions, and we have seen those 7 transition, but the intensities do not agree with the field spectra. Do you get artifacts at the edge of the... I see. So yes. Yes, I think we get the artifact at the edge.
Okay. Are there other questions from the audience? Okay, I guess not. Then we can close here the seminar, and the appointment is for the next one in 2 weeks is about pulse DMP, and we'll send the announcement in a week or so. All right, thanks Manoj, thanks for the to everybody for attending the seminar, and yeah. I'll see you in the next one.
Thanks for the opportunity.
Bye.
Bye-bye.